Hi, today we will represent a new perspective on soft object perception based on the idea that our perception of soft objects relies on abstract object representations that incorporate intuitive physics. I'm Wenyan, and this is Olive, and we will present our joint work with Kimberly Wang, Brian Shao, and Yoker Yildirim at Yale University. While encountering soft objects, we not only perceive low-level properties such as colors and orientation, but also seemingly higher-level ones, which includes many aspects of physics, such as softness, elasticity, and mass. We see these physical properties not in isolation in the abstract, but as parts of the soft objects, as things that we can cut, fold, shape, push, pull, slice, and throw, as things that we can manipulate in many different ways. What are the sources of these rich soft objects perceived in the mind that supports such flexible and creative action? Most existing work in material perception focuses on delineating which image cues or patterns are associated with these mechanical or optical material properties. For example, it has been shown that visual cues in the form of image statistics and mid-level perceptual features are important for the estimation of physical properties. But here, we ask a different question. How are these physical properties represented in the mind in a way that they can support such rich and generalizable perception? To this end, we propose that visually estimating physical properties of class must involve not only image statistics or perceptual features, but also abstract object representations that incorporate intuitive physics, which is a physics-based representation that explains observed shape variations in terms of how unobserved object properties determine class reaction to external forces. In this perspective, perception of soft object properties such as mass and stiffness is to go from these observed shape variations to a small set of physical properties that can causally explain these observations. Today we present our project in two parts. First, we talk about the novel human data we collected, and then we discuss various models' ability to account for the data. Our task is very simple. On each trial, participants see 3 class videos from different scenarios, and they are asked to match the stiffness of the class from the target video, which always presented on the top, to one of the other two, both represented at the bottom. The class that matches the target in stiffness is called as the matching class, while the other one is called as the distractor. We tested for different scenarios, each showing the class interacting with a unique type of external force and going through certain natural transformations. For class in each scenario, we varied both the stiffness and mass values in a log linear space. As shown here, from left to right, the class becomes stiffer, and from top to bottom, the class becomes heavier. Using the stimuli, in the visual matching task I introduced a couple of slides back, we measured how humans generalize their stiffness estimations across scenarios. In this task, we controlled for the stimuli such that the 3 videos on each trial were always from different scenarios, and their mass values were randomly assigned. We collected data from 17 participants. Their average accuracy across all trials was 67%, which is significantly higher than the CHESS level of 50%. To discern the effect of scene on stiffness judgment, we iteratively held out one scenario and computed the average accuracy on the remaining 3 scenarios. As we can see from this bar plot, even though there is some variability, there is no significant difference between these 4 scenarios, thereby indicating that scenario does not affect the performance. Next, we take a closer look at human accuracy for each stiffness pairing. Here, the x-axis shows the stiffness values of the matching class, and y-axis shows the stiffness of the distractor class. Upon filling in all values, we can see a faithful degradation of performance as the stiffness values of the matching and distractor class become similar. This graph shows that this relationship is log linear. Average accuracy log linearly decreases as a function of the difference between the stiffness values of the matching and distractor items. Together, these behavior results suggest that humans are able to generalize across scenarios and mass values. Next, We will use these results to test alternative computational approaches.
The first computational model we consider is a deep convolutional neural network (DCNN). We sought out to test the ability of the DCNN to account for the cross-scenario generalization required by a novel stimuli dataset and evaluate its ability to explain human behavior. For this project, we used an existing DCNN architecture that has been shown to predict human viscosity judgments and set up its architecture to perform the regression task of predicting the cloth stiffness in log scale. We constructed a training dataset for each of the four scenarios where the stiffness for the stimuli were randomly drawn from the five testing stiffness values, and the mass values were randomly sampled. We introduced geometric perturbations within the initial configuration of the cloth and the colliders such that the overall integrity of how the external forces acted on the cloth was preserved. The testing dataset combined the videos that we used in the behavioral task. We trained the DCNN architecture on all four scenarios and also tested it on the same four scenarios. Note that as the training and the testing data differed only in terms of small geometry differences, the model requires minimal generalization. Thus, this model can be seen as an ideal observer model as it approximates the upper bound on signal in the sense inputs to perform the task, using the DCNN as a universal function approximator. We can see that now, under this minimal generalization requirement, the DCNN accurately predicts the cloth stiffness both in the validation set as well as the test set. We also consider testing cross-scenario generalization in this DCNN architecture, where we trained the architecture just on three scenarios and tested it on the held-out scenario. We can see that even though this model performs well on the validation set, it completely fails when it comes to the untrained scenario, thus failing at cross-scenario generalization. Because the second approach fails in our work, we will only consider the first kind of training that we did with the DCNN, the one where we train the DCNN on all the four scenarios and the one that requires minimal generalization. Next, we considered a new model that realizes the hypothesis that perception of soft objects is based on approximate probabilistic inference in a simulation-based generative model. The core of this generative model is a stochastic physics simulator that represents cloth as particles with assigned mass values that gives rise to the area weight of the cloth. Each particle interacts with its neighboring particles with a small number of particle-to-particle interaction rules that induce stiffness to the cloth. The cumulative effect of all of these interactions, in addition to the external forces acting on the cloth, induce 3D shaped variations. Thus, we posit that to visually reason about the underlying physical parameters of the cloth from its shape equates to inverting the generative process of how the cloth was formed in the first place. This diagram shows how we realize the hypothesis, including the process of selecting a scenario, randomly sampling the physical properties, including the mass and stiffness, and unfolding the scene over time through particle dynamics. But perception is to invert this process, is to go from images to their underlying representations with respect to this generative model. We model the perception using standard sequential Bayesian inference method, where the model at each time step observes 3D geometry information of the cloth and dynamically propagates an estimation of the cloth stiffness and mass over time. In this work, we found that accurate inference can be implemented using a particle filter with only limited computational resources. Here we see the performance of this model. Similar to the DCNN, there's quite a high correlation, but not as high, between the model's predicted stiffness values and the ground truth parameters, with an R-square of 0.61. Moreover, we can see that the internal dynamics of this model integrates sense inputs over time. On this graph, you can see that the model's estimate of the stiffness become more and more accurate as time progresses in the video. The mean squared error to the ground truth parameters reduces and the correlation to the ground truth parameters increases gradually over time as the model observes more evidence. Here, to show an example from the drape scenario to illustrate how our model integrates evidence that emerge from the observation. The three cloths shown here have the same stiffness but vary in their mass. The mass decreases as you go from left to right. We can see that the heavier cloth falls faster as compared to the lighter counterparts due to the air drag, suggests that there is ample evidence for mass for the cloth during this time. Additionally, we can also see that the cloth barely stretches or contracts while freely falling under the influence of gravity, and therefore there's little evidence for its stiffness until it interacts with the flow. Here, we plot the mean squared error of the model predicted stiffness across all particles and chains during the time courses of the cloth videos. We can see that the particle filter quickly converges to the ground truth stiffness only after the cloth interacts with the flow.
Now, with the alternative models at hand, we can make comparisons between the error patterns of these models and behavior. This tau plot is from before, showing the average accuracy of humans for every possible pair of stiffness values between the matching and distractor items. And this is the tau plot showing the performance of the DCNN model. And this is a tau plot showing the error patterns of the physics-based model. Similar to humans, we can see that both models performs better than chance, although the DCNN model makes very few errors relative to the physics-based model and behavior. We can directly compare models and humans by correlating the entries across the taus. We will compare the human behavior to the DCNN model. We can see that they are unrelated with an R-square value of 0.09. However, when we compare humans and the physics-based model, we can see a very strong correlation with an R-square value of 0.64. This result provides evidence for the physics-based model of soft object perception. We can take a closer look at how the accuracy changes as a function of the stiffness difference between the matching and distractor items, again comparing models and behavior. Here we can see that both the physics-based model and human behavior show a log linear relationship between the accuracy and the stiffness differences. But for the DCNN model, this relationship does not hold.
But, Wenyan, wait, can you truly make any conclusions from this? Like the poor correlations of the ideal observer model could simply be because it's just way too good at performing the task. Have you tried a version of the model where you terminated its training entirely as soon as the overall accuracy of the model came very close to that of the humans? Maybe then the overall trend of the TCNNs would be similar?
That's a great question, Alok. I did train a number of other networks that match the overall performance to that of the humans, and now I'm going to show you the results of these performance-matched networks. On the right, you will find that the overall accuracy of such performance-matched DCNN is comparable to that of the humans, which is 0.66. We trained multiple performance-matched DCNN, and so far we found that controlling for performance in this model did not improve its behavioral fits. Here you can see that the average R-square of multiple such models still remain low at 13%. Last, we use multidimensional scaling to compare how the different class videos are represented by each model and the humans. We can see that physics-based model is more consistent with behavior in terms of how the stiffness values are clustered than the DCNN model. To conclude, today we presented a new computational framework for soft object perception and used it to provide evidence for physics-based object presentations in how we perceive cloths. But there's more work to be done. Our model presently accepts 3D mesh information for stiffness inference, but we plan on extending our model to make image computable inferences. Additionally, we want to understand if stiffness is special or do humans also predict other physical properties like mass in a similar fashion. To this end, we intend to perform additional experiments, both behavioral and neural, with which we hope to unravel the nature of neural representations that underlie our rich percepts of soft materials, and how those rich percepts in turn support the flexibility of physical material perception. We thank all of our collaborators, Kimberly Wang, Brian Shao, and Yoker Yoderam. And we also thank our fantastic labmates. And thank you so much for listening.